All right. So our next speaker is Kimmy Wu, Associate Staff Scientist and Panofsky Fellow here at KIPAC. Kimmy also has a long history with KIPAC, being a grad student here a long time ago, 2009, 2015, working with Shaolin.
I'm not that old.
Sorry. And returning to KIPAC in 2020. So Kimmy is a cosmologist and an expert on everything CMB, from theory, data analysis, and instrumentation, in particular focusing on cosmic microwave background lensing, primordial gravitational waves and inflation from the CMB, and recently using machine learning methods to analyze it. So please take it away.
All right, thank you very much for the kind introduction and for the opportunity to talk about a topic that's near and dear to my heart, the cosmic microwave background. So at KIPAC, we have a very strong group of folks working on CMB and CMB adjacent topics. So I'm sure if you ask each one of them what they think are the most important developments in the last 10 years, you'll get different answers. So this talk is really about what I think are most interesting. But one of the things that I like you all to take away is that while different people might have different views of what are the most key interesting things from CMB the last 10 years, CMB I think is pretty uncontroversially true that it serves as a foundation for modern precision cosmology. And that it really is a unique probe to a few things in fundamental physics going forward. So it will be a frontier for cosmology going forward in the many years as well. So let's dive in. So this is a cartoon of the history of the universe. I'm sure many of you have seen. And in previous talk, we have Simon and Juna talked about how we can map all the galaxies so when they are first formed, and then if you move back in time some more, and if you're a photon, then you'll inevitably hit a wall when what we call the CMB, the time when the CMB was formed at recombination. So what happened was that, so you know, the universe has been expanding. So if you dial back in time, it got smaller and hotter and denser. It got so hot and dense that no stable helium or hydrogen were around. What that means that instead of normal atoms, you get electrons, protons, all these charged particles around. So if you're photons, you get just bounced off of that because you have a large interaction cross section with these charged particles. So that was the era when the CMB was formed. So let's think a little bit about this, what that means. The universe was really hot and dense, and you get tiny fluctuations of matter over and under density. And you're a photon, you are very tightly coupled with normal matter because of the scattering. And so whereas hotter or colder, your temperature when you got released from the bath could be hotter or colder. What that means is, as we observe and make maps of the CMB, we can learn a lot about the state and the content of the universe at the time. And what's more is that not only can we learn a lot about the universe at the time of recombination, if you travel back in time some more, at the earliest 10 to the minus 32 seconds of the universe, we cosmologists postulate that the universe had gone through a near exponential expansion, we call inflation. And as it turns out, there are these generic predictions of inflation where there were these gravitational waves generated, and they leave imprints on the CMB itself. So we can probe to essentially the earliest moments of the universe by making an observation of the cosmic microwave background. Now, so we have walked back in time. So let's play the movie forward. The CMB not only had it seen early parts of the universe, it also had gone through the rest of the history of the universe before it gets to detect us. So what that means is that structure at form, you have deep gravitational wells, and as Chiwei had mentioned, the paths of the photons got deflected as it goes through gravitational wells, and it got lensed. And also, if you happen to run into a big galaxy cluster, they are hot gas, so you will get inverse Compton scattered, so your spectrum change a little bit. So we get all of that information from observing the CMB. So really, the CMB is quite rich, or just in general, millimeter wave observations will give us and do give us a really rich data set to explore and play with. So let's take a look at what some of the maps look like. So this is a simulated CMB map before it got lensed. This is 10 degree by 10 degrees. And the fluctuations is relative to the mean CMB temperature of 2.7 Kelvin. So these large blobs, these scales is about 1 degree on the sky. And to give you a sense of scale, the moon is about half a degree on the sky. So these large positive and negative temperature fluctuations you can see are essentially the largest, strongest power you can measure in the CMB temperature and isotropy spectrum. Now, if I click on and show you what the lensed CMB map look like, you get a little shift going back and forth. So it's a small effect. And now on top of that, as I mentioned, we in the millimeter wave, we see all the rest of the processes as well. So I'm going to overlay what we call CMB foregrounds on this map. So you see little dots pop up and a bit of a difference in the DC scale of this map. So these are small effects with these foregrounds. However, the point is that our CMB experiments these days are so sensitive that we can actually leverage these maps of these foregrounds to study cosmology. So a few of the key foregrounds in the CMB temperature sky is 2 of them from the Sunyaev-Sottovich effects, the temperature, the thermal SZ, and the kinetic SZ. Then there are emissive sources in these wavelengths, the cosmic infrared background. So these are dust emission within star-forming galaxies, and also radio sources. So these could be AGN or synchrotron sources. And this gives you a sense of the richness of this data set. And I haven't even got to what the emissions within our own galaxy or transient sources that we can observe with a millimeter wave telescope. All right, so I mentioned that CMB really do serve as a foundation of modern precision cosmology. And the key experiment that brought us that really is the Planck satellite, of which KIPAC faculty member Sarah Church was a member, and her work may enable this measurement. What I'm showing here is temperature and isotropy spectrum from Planck, and about where you see the peak is about 1 degree on the sky. So by eye, the positive and negative fluctuation you see on the map causes that peak. And that corresponds to the sound horizon at the recombination. So that's actually one of the most precisely measured cosmological parameter we have to date. So I talk about, and we heard of lambda CM a lot in its simplest inclination. There are 6 free parameters, and CMB constrained them all. Angular size is one of them. And from the angular size, we can write down what the Hubble constant is today. So then we can also learn about the matter and baryon density from the relative peak heights of the second and third peak. So this is evidence for dark matter. And overall scale and tilt of this spectrum tells us the primordial scalar spectrum amplitude and tilt. So there are 5 parameters here. The 6th one is the so-called optical depth to reionization. It's mainly constrained by the polarization of the CMB. You can get it from the temperature and isotropy spectrum as well, but not to as high a precision. And 5 of these 6 lambda CDM parameters are measured up to sub% precision. And this is really a testament to the feats of the engineering and science excellence of us scientists. However, as is alluded to earlier in this session, the more precise you measure something, the more likely that your measurement will disagree with someone else's measurements of the same kind. So this is kind of the state of our lambda CDM model right now. These are very busy plots. On the left, show the Hubble constant, so that corresponds to the expansion rate of the universe today, and on the right is SA parameters, which corresponds to roughly fluctuations in the matter density. The key takeaway here is that where it's from the top. So these are early universe measurements of these parameters, and at the bottom are kind of late universe measurements of these parameters. They don't agree to the statistical precisions that are being measured from different surveys. The more significant tension is on the H0 side. So it could be from 4 to 6 sigma, depending on the exact measurement. The SA tension is kind of 2 to 3 sigma consistently, but also there are new results coming out that is showing that potentially there is not really a tension. So this is to be continued developing story. Stay tuned. But this really spurred a lot of creativity in the theory side of asking the question: what new physics could there be in order to reconcile these differences in the way that the parameters come out? Is it just a systematics in the measurements, or do we need new physics? Is lambda CDM breaking down? Now, this paints a picture of how CMB really serves as a foundation for modern cosmology. The new frontier really is pushed by ground-based experiments. And in 2 fronts in particular, by providing really deep polarization maps and also really precise lensing maps. So in the background are 2 pictures of sites that we commonly deploy CMB telescopes at the Atacama Desert at Chile, and also at the South Pole. The reason why the ground-based telescopes are really making headway in this field is because we're able to pack a lot of detectors, because even if it is super heavy, it's okay. We just ship it on a mountain, go to the South Pole. We don't need to send a rocket up to space. And also we can really build the big dishes, and we don't have to send it up to space. So we can make really high resolution millimeter wave maps. And next, I will be talking about results from the BICEP-CAC collaboration and SPT, the South Pole Telescope experiments. They're both located at the South Pole. So I'll first talk about deep polarization maps, then I'll talk about the really precise lensing maps that we have. For the deep polarization maps, one of the really cool goals that our field has and is working towards is to be able to search for this elusive primordial gravitational wave signature from inflation. So this is a power spectrum I've shown. You've seen the teapot measured from Planck. And then in the red is the EMO polarization, and in the gray dotted is in the BMO polarization. So the CMB turns out to be polarized, and in lambda CM we expect the EE spectrum, and inflation and the primordial gravitational wave are essentially the only source that will produce a detectable, potentially detectable BMO signature, the primordial BMO signature. So the E modes are divergence-free, curl-free, and the B modes are divergence-free, so it has a curl back pattern. So what is R? R is related to the amplitude of the primordial gravitation waves, and they specifically as a ratio of the primordial tensor to scalar spectrum. So a detection of primordial gravitational waves will be really strong evidence for inflation, and it also probes physical processes that are at these extremely high energy scale. That's just inconceivable to be able to be reproduced on Earth. So it will be quite incredible to be able to see signatures of that in our own CMB maps. Now, as you can see, the y-axis is in the log scale, and so the B modes for these 2 levels of R that I've plotted is already way smaller compared to the temperature and isotropy spectrum you've seen by eye, and also the maps you've seen by eye. These are fluctuations smaller than 10 nanokelvins or so. These are tiny signals. Makes it very hard to measure. In addition, our own galaxy emits in the millimeter waves as well, and they are polarized. So these foregrounds on the cleanest patch of sky is already overwhelming our beam modes potentially from primordial gravitational waves. And we have no idea how small it is. Our current upper limit is already less than R of 0.1. So the deepest polarization maps at the degree scales come from the bicep Keck telescopes, and many of the KIPACers work on these telescopes and are part of this collaboration. So very quickly, these are small aperture telescopes. This focal plane there is about this big, and bicep arrays are currently developing experiments that has essentially 4 copies of bicep 3-like telescopes on the mount, and it has different frequency focal planes so that we can differentiate the galactic foregrounds from the CMB. And a quick shout out of KIPAC folks who are who work on the high frequency receiver of bicep array at the basement of PAB. So if you get a chance and know any of the grad students on bicep Keck, ask them for a tour of the telescope. Now let me show you some maps from our latest result. So this is maps of bicep 3 and also a previous generation stage 2 program, bicep 2 and Keck, and the E modes and the B modes at 90, 150, and 220 gigahertz. It gives me particular joy to look at the bicep 3 maps of the sky, not only because it's super high signal to noise, it's also because I was a wee grad student working with a small group of people locally here at KIPAC, and also in the basement of PAB to develop the bicep 3 receiver. From this set of maps, we are able to actually extract wall-leading inflation constraints. So this is a pretty busy plot, but all you need to focus is the top left corner, where the R upper limit we extract from our latest result, improvement from the red set of posterior on R. And the rest of the parameters constrain galactic foregrounds. Now, what are the implications on inflation? So on the y-axis here is R, and the x-axis is NSBS, which is the tilt of the scalar spectrum. With the blue, going from the green to the blue is whether we include the bicep Keck results. And the orange band is single field slow roll monomial models. They are well excluded as a result of the upper limit provided by the bicep Keck collaboration, bicep Keck maps. So it's really quite incredible, because typically when we learn about inflation, we have a textbook example of phi square potential, and this is already very strongly disfavored. Now that's spurred our theory colleagues in SITP. So a couple of weeks after we put out this result, they come up with this alpha attractor emo models that happen to have their peak of to predict R at the peak of the posterior distribution of our marginal posterior. So this is one example I thought is super beautiful, where theory and experiments really push each other so that we make progress in science. And I really should hurry up. So that's not the end of our research. There is a class of really well motivated model for R, so that we want to push forward to be able to constrain R even better. And our next biggest challenge is to remove this lensing-induced B mode that is in the black solid line. And in fact, the tightest constraint I just showed you is already limited by the uncertainty from lensing. And going forward, we delens with SPT 3G data, and we expect to be able to improve uncertainty on R by more than a factor of 2.5. And so in this process, what that means is that we have to characterize the whole process very carefully to make sure that there are no biases. So this is extremely terrifying and exciting. Now onto lensing maps, which I think really is one of the key frontiers of cosmological information. Very briefly, CMB lensing, we observe a lensed version of the original primordial CMB field, and the amount of deflection can be encoded in this phi field. So the CMB lensing potential. So the amount of deflection is the gradient of phi, which is a weighted gravitational potential integrated along the line of sight. And one thing that I recently got reminded of and got really excited about is that it turns out adding now with upcoming CMB maps and surveys, adding CMB lensing to our cosmological parameter inference significantly improve the uncertainty on some parameters. So this is an example of sigma 8 and H naught with and without CMB lensing. It used to be that you just take Planck CMB primary, and that's the most of the information you get for cosmology. But now adding lensing actually significantly add more. So I get quite excited about that. There are two key ways that ground-based CMB lensing experiments already surpass Planck's lensing experiments. One is the per mode measurement sensitivity. So if you look at these lensing maps, where it's positive and negative, these are measured to highest signal to noise compared to the Planck satellite. And also the lensing spectrum uncertainty is measured to higher signal to noise than the Planck satellite. And one thing to call out is Frank, who led this analysis, is coming to KIPAC in the fall. So let me flash a really new result that we just put out a couple of weeks ago from SPT3G. This is first SPT3G lensing result, work led by Javi and Federico, who's local. So here is a lensing kappa map. And on the left is the cosmological parameter constraints when we combine it with BAL in the dark red colors. The key takeaways is that the lensing measurements is consistent with primary CMB inference of these parameters where in the shaded region. And also one thing I like to point out is that this analysis used data from just half as observing season of the new SPT3G camera. What that means is that we have a lot more data in the can. And with just half a season of the observation, we get as constraining a measurement on lensing as all of the previous SPT lensing maps. Finally, maybe not finally yet. So next, what we are going to do is we have that deeper data in the can. I'm really excited about this next lensing measurement by work led by grad student here and KIPAC postdoc here, Yuka and Yuki. We expect to have the highest signal to noise per mode measurement and also really competitive lensing spectrum measurements. And I can talk about the Y field survey at lunch. New opportunities. We do a lot of summary statistics, but with the advance of computing and machine learning, really one of the frontiers that we'll be able to explore is to use field level inference and be able to just use all the pixels and model all of the information and be able to use these foreground information to understand cosmology and astrophysics. Because as you can tell from your eye, these fields are not Gaussian. So summary statistics is not going to capture all the information there is that our telescope give us. Now, let me summarize. This is a partial view of CMB progress from KIPAC at 10 and KIPAC at 20. It used to be that the gold standard of lambda CDMs from WMAP. We now have Planck as our gold standard. And the measurement uncertainty is so small that now new fields get developed from it. Are there new physics required to describe cosmology? Is lambda CDM breaking down? It used to be that the best upper limit from R comes from the large scale temperature fluctuations in the CMB maps. Now our B modes are measured to high signal to noise, and that leads the R upper limit. We used to just had several sigma detection of the CMB lensing spectrum. And now the ground-based CMB lensing spectrum measurement has surpassed the most precise one from Planck. And 10 years ago, I used to be a wee grad student, and today I get to give this talk. So I'm really excited with all the people that's going to be here working on CMB and CMB adjacent fields. What will the next 10 years bring? These are some pictures of experiments operating and to be deployed, and a big stage 4 experiment, CMBS4, that we're working on. So I'm confident that we'll get to study all the history of the universe from its beginning, 10 to the minus 32 seconds through now.
Thank you, Kimmy, for the really nice talk. Questions for Kimmy? I know there's a lot of questions.
Yeah, I go
CMB.
over things very quickly.
If not, I can start with. Oh.
That's probably a silly question. That's its detection supposedly by the guys with the pulsars. The pulsar array is the detection of background gravitational waves. How much does this get into your B modes? Does this have any influence or not?
Yeah. So that's a great question. So the PTA, the frequency that they measure the gravitational waves, is quite a bit higher compared to the band that CMB is sensitive to. So for inflation in particular, if the model predicts a really blue tilt of the tensor spectrum, there's a possibility that what they measure could be primordial and inflationary. And because of the really rather tight upper limit we already have from CMB, we know that the amplitude of primordial gravitational wave, if the spectrum is not tilted, is flat, what they are seeing wouldn't be primordial gravitational waves. So in other words, either without any other sources of sourcing those, which more likely would be binary black holes, the statements we can make about inflation with their measurements is that it's plausible that we have a very blue tilt, though that does violate the very simple single field inflation model.
Gregory.
So I think I have a kind of depressing question, but is it possible that the actual B mode, the primordial B modes, are actually just so faint or so weak that given the backgrounds, they'll just never be measurable? Or I guess put another way, what is the smallest R that we could actually measure given the strength of the foregrounds if you had like all the money in the world, and if we were 50 years in the future? Is there like some limit?
Yeah, I don't necessarily think that there is. So I think we can always push deeper and characterize foregrounds better. There will be other sources of B modes as well. So for example, from reionization, we expect B modes, and also just simple from beyond linear order of E, even from lambda CDM, we expect B modes. Those are much smaller. So at that point, you also content with these other sources that you have in the model. Yeah.
Thank you. Any other question, Chiwei?
Hey, Kimmy. So I want to ask you about your recent realization of how lensing helps primary CMB. So yeah, can you just say a little more what is adding to it? And is this the main parameter space that it does anything?
Yeah, so the key thing here actually is the ability to be able to measure sigma 8 much better, because it's a direct probe of the late time matter fluctuation. So it turns out then because of the improvements, sigma 8 improves omega matter, and as a result, it improves H0. But then it gets to do very interesting questions of, let's say if we get to smaller scale measurements of the lensing spectrum, how there is the complementarity with optical surveys, what we might be able to probe.
Great. Thanks a lot. So thanks again, Kimmy, for the next talk.